Hi everybody, welcome to a new video. In this video we're going to talk about shaders again. And we are talking this time about shaders using the new GL3 package, which allow us to use shaders not anymore in the 1.2 version, but using actually the 3.3 version of the GLSL language, which has some differences with the version 1.2 that was previously used in Max previous to the GL3 package. So we are going to do a series of tutorials, so you and me all together we can understand better how to write shaders using the new language, the new version of the language, let's say, and we are going to see hopefully some interesting shaders. And this is also important for us in order to see how the API of Max communicates with the shader program and what we have to declare inside the shader in order to access some variables and stuff. So this will be pretty useful. So we are going to start with a lighting shader, so a Phong model light shader, which basically is a shader that renders the object using a diffuse, specular and an ambient light that gives this appearance. So for example in these three spheres, every one of them has the same shader, so they all have a specular light, they all have a diffuse light, which is basically their color, and they all have an ambient light, which at the moment is kind of black. The ambient light is basically the light that is applied to the object independently from where the light it is. So it's basically just a color that we sum to the object color itself. Okay. So this is the first video of this series, and I'm following a book called OpenGL 4 Shading Language Cookbook. So I will follow this book to get some references about shaders and some ideas, and yeah, basically the shader code. And we are going to explore together how the math of the shaders work and how they logically work. So let's start with the Phong model lighting shader, a simple Vertex Shader version. So this is not the calculations are not done inside the Fragment Shader; they are done inside the Vertex Shader, which makes the shader a bit more performant, but it doesn't give us better results as if we would do the calculations in the Fragment Shaders. But this doesn't matter because in the future we are going to see also how to implement this in the Fragment Shader. So yeah, we are going to get a lot of information about how shaders work in the 3.3 language. So let's start. So what I will do is to put this patch on my second screen. All these fellas. And I'm going to create another patch from scratch. So I've saved it, and I will just create a Git world. I will call it shad GL3 shad, and I will give it FSAA1, and I will give it some window position. I will give it some window dimension, which is the attribute size, and then I will give it some race color 0.2, 0.2, 0.21. Then I would say I will give it the floating one attribute to make the window always stay on top. And maybe I will also say FPS 120. Since this is the refresh rate of my screen. Okay, and then let's touch toggle. Let's also create a camera. TGL camera. GL3 shad. And let's say position 003. Look at 000, so we'll always look at the center, tripod 1, so it will not tilt, and lock 1, so it will always look at the center. Then let's actually connect this to a git anim drive, so git.anim.drive, let's say UI listen, say speed 20, so it's a bit faster. Let's connect this to the camera. Let's connect the message anim reset both to the camera and to the git anim drive, so in order to get the camera back to the original position. Okay, so this is good. Now let's create a grid shape. This is the object on which we are going to apply our shader. So let's actually create GGL grid shape. So GGL grid shape, GL3 shad, shape sphere, and let's say maybe color 1111. That's it. We can increase the dimensions of this object. So 200 by 200. So it's pretty smooth. And yeah, for the moment, that's it. So we could also say here light enable. Then we will have a nice lighting shader applied to this object. But our objective is to create the lighting shader ourselves. And why do we want actually in the first place to create the light shader ourselves? Because if we then want to modify the shader to add some more functionalities that is just not the light, we have to create the light shader first and then add the different functionalities on top. So the light shader is kind of the basic step that we need to create. That's why we are starting with the light shader. So let's actually create the shader object. GL shader, GL3 shad. Let's give it a name. So let's call it Phong Shader. And let's give it a file. So let's call these Phong shad tooth.jxs. This file doesn't exist, of course. So we are going to double click on the object. This is the default shader that we get. We are going to save this shader, calling it as we called the file name. So what's the file name again? Phong-shad-tooth.jxs. So, Phong-shad-tooth.jxs. Cool. Then let's apply this shader to the grid shape. So let's say shader Phong shader, and the geometry is gone. Disappear because the shader basically it's not set to render a simple shape, because there is a geometry shader here. Let me actually open the shader with an editing program. So we'll use Visual Studio Code. So a code text editor. Instead of plain text, let's say GLSL. Cool. So that's the shader that we get by default. As you can see, it contains geometry shader, which we actually don't need at all. So let's proceed and delete the complete geometry shader. So after the vertex program, after the program closing tag, there is program name GP. We start from here. We go down to the closing program tag and bam, delete all of it. So we just have now, we just got the vertex shader and the fragment shader. As you can see, the shape has been rendered. For example, if we want to check if the shader is actually working, we can change the color of the shape by creating a vector 4. For example, let's make it red. So let's make 4 numbers. The first one is the color for the red, second is green, third is blue, and last one is the alpha. So they all go from 0 to 1. So as you can see, it's working because we can make our shape red. If we add another one here, it will get yellow, and so on. Okay, so this is actually working. So let's actually re-put inside jitin.color, which is actually the color that we pass to our shape. In fact, if we go into the attributes and we say GL color, we can see that by modifying this color, we are actually modifying the variable color inside the shader. So let's see how does it actually this variable get inside our shader. Well, you can see that it's passed as a parameter, and it is passed as a state parameter. So it's not a uniform parameter that we send to the shader as a param. This is actually an attribute parameter. So it means that differently from uniform parameters, this is an attribute parameter which means the change for every vertex, while a uniform parameter, so it's the same for all the vertices. So let's actually make this distinction. So attribute parameters change for every, or could change for every vertex, could be different for every vertex. And then we got uniform parameter, which are the same for all the vertices. Okay, so this one here, the color is actually an attribute, because this, we could have a, for example, with a GGL mesh, we could have a matrix that sets a different color for every vertex. So this is how the color is linked into our shader. From the shape, this is passed into the shader. So let's take 1 second a look to what we got inside the shader here kind of declaration. So first of all, we, like in a shader written with the 1.2 language, we got the name of the shader. So let's actually call it Phong shader. And then description, we can actually leave it blank. And then we got some parameters that are either coming from the state from Max API, or they come as uniform parameters. So let's see how we can declare the ones that come from the API, and now we can declare the ones that come as parameters. So first of all, we can see the first parameter is called position, is of type vec3, and it comes and is a state parameter. So this is actually an attribute, which means that it's different from every vertex, and this contains the position of every single vertex. But the position is contained in object space. Now, if you don't remember what object space means, I suggest you to visit my website, where I have an article, Introduction to Shaders, which basically will explain you everything about a bit how shaders work, which this was done for GLSL 1.2, but it's basically a lot of the concepts are basically the same, because we still got a differentiation between model space, world space, and camera space, and this is very important to understand. So it's important to know that this position is actually in model space. Okay, then the second parameter that we have is also a state parameter, but this is actually a uniform, because it's actually not different for all the vertices. This is actually the same for all the vertices, and this is the model view projection matrix. So this is a matrix that will transform our objects from object space into projected space. So basically we'll transform them from the coordinate set of the object itself to the screen coordinates. Okay, then the third one is the color that we mentioned before. So let's actually put these after the position, because these are all parameters that are related to the object itself. This is the model view projection matrix, actually not related to the object itself. And then below here we have the binding of those parameters. And as you can see, they're all binded to the Vertex program, which is actually what we want. So, okay, inside the shader, the first shader we got is the Vertex program, so which is the type Vertex. This is the Vertex Shader. As you can see, there is a declaration which declares the version as to be 3.3 core. Core means that it will not use the functions from GLSL 1.2. It will use only the core functions, so only the functions included in GLSL 3.3. As you can see, we declare the model view projection matrix that is here as a uniform. This is a mat4, as you can see, which means it's a matrix. It's not a jitter matrix, that's another thing. This is basically a mathematical matrix with 4 rows and 4 columns. And then we got the position as an input vector. This is a vec3 because the position is x, y, and z. And then we've got the color as a vector 4, because as we saw, this is the values for the amount of red, green, blue, and alpha. Okay, then what we've got here, this is a structure. Now this is actually, yeah, it's kind of a structure that defines what is going to be the output of our Vertex Shader. And this is something that we didn't have inside GLSL 1.2. This is something that goes on from GLSL 1.5, so Before, we just had to fill like the GL position, and then we could send the parameters in, send the values in output using a varying variable. But in GLSL 3.3, we've got actually input and output. So an input is what comes from the previous stage of the pipeline, and in this case, this is basically the max API. And what goes out goes to the shaders after it. So before there was the geometry shader, which we deleted, and now it will just go on to the fragment shader. Okay, so this output structure will be the input structure inside the fragment shader. Okay, that's it. Now, inside the main function of the Vertex Shader, we see that we multiply the model view projection matrix, and we multiply this by the position, but we transform this first into a vec4, because a mat4, like the model view projection matrix, can only be multiplied by a vec4. And it's also important to understand that the order this multiplication happens is important. So it's not commutative, I believe you say. So it means that there is a difference if we multiply first the vector for the matrix or the matrix for the vector. As you can see, now that I put the matrix after the position, the result is completely different. This becomes kind of an oval. I mean, the projection is completely wrong. So it's important that the matrix is actually added first, and then is actually written first, and then multiplied for the position, and the position must be after. Okay, it's not a commutative multiplication. Okay, so going on, we see that we are passing out the color, filling it into the JIT_out structure.color variable. So this is this variable that is written here inside the JIT_out structure. So this is like a class. We are basically accessing the property color of the structure JIT_out, and we are setting this value to the values of color that we are getting from inside from the Max API. Okay, so this was the end of the Vertex Shader. Let's go on with the Fragment Shader. And as you can see, we declare the same structure as we used in the Vertex Shader, but this time, instead of being an output structure, is an input structure, and we call it JIT_in. So the color is set to the value of JIT_in color. As you can see, there is a vector for color that is declared as the output, which means this will go into the successive stage of the pipeline, on which we anyway don't have any power anymore, because this is going to go to the renderer that we then basically render the shape inside the window. Okay, cool. So let's now see what do we actually need to write our light shader. Okay, first of all, we are going to need a couple of things. For example, we are going to need the normals of the shape. Now, the normals are vectors. I think I explained this in some tutorials before, but basically the normals are vectors that are perpendicular to the surface. So you have to imagine this shape covered by vectors that go outside the surface, a bit like an hedgehog, and they are basically perpendicular to the surface. Okay, so this is used, the normal is used into the light calculation. Because as we know from tutorials about shaders and light, the light amount on the surface, so at this vertex position, here, which is basically where the normal, from where the normal steams out, so let's say at this point here, this is our vertex, so with this normal, that's the light source. And the intensity of the light at this point is basically calculated by the dot product of the normalized vector normals and the vectors of the light to the shape. So the dot product of this angle here will give us the intensity of the light at this point. Okay, so this we are going to see in a second, but this means that we need the normal at this vertex to calculate the light. Okay, so let's actually get the normal. The Max API provides us with the normal, so we just have to get it from it by declaring it as a parameter here in the shader declaration. Let's say so. Let's call this normal. type. We know that the normal is a vector 3 because it's an x, y, and z components. And then state, and this is called normal. Now, these names that you see here, these I have not invented. These you have to write exactly in this way in order to get the right value from the API, okay? So everything that comes with state, you have to write exactly how it's written here. This is in the Max documentation. Okay, so let's go into the binding phase, and let's bind normal to program. And the program will be the Vertex program. Right. Okay, so let's declare the normal also as an input vector here. So normal. And very nice. Oh, what we can do, we can actually try to visualize those normals as a color. Maybe. Let's try by passing them onto the fragment shader. So let's declare this as a flat vector. Now flat, it means that this vector is not going to be interpolated between the vertices in the fragment, in the passing from the vertex shader to the fragment shader. Usually variables get interpolated for every fragment, but if we write flat, this interpolation doesn't happen. This interpolation is basically what gives us a smooth lighting when we write smooth shading inside the GL grid shape, so the attribute. Okay, we can choose to not interpolate by writing flat. So let's say normal, and then let's write, oh yeah, there is surely an error because we didn't declare this into the input structure on the other side. So let's write git out normal equals to normal. And then here let's write flat back3 normal, and this should actually stop the errors, right? So let's, instead of writing git in color, let's write git in normal. Of course this must be a back4, so let's create actually, because color here, our output is a vector 4, so this must also be a vector 4. And GLSL is intelligent enough to just understand that this is a vector 3, and then we can add another component to make this a vector 4. Okay, cool. Now, as you can see, this is the value of the normals of our shape. Okay, so the blue color basically means that the normal, let me actually reset the camera. Now the blue color, it means that the normal has a bigger zeta component. The green color means that the normal has a bigger y component. And the red color means that the normal has a big x component, right? So this is why we are seeing actually these values. And on the other side, they are going to be negative, so the biggest component is going to be a negative number. That's why we see black. And that's it, we are visualizing the normals through the shader. Okay, actually this video is already getting a bit long. I would like to keep them kurz und knackig, as you say in German, so basically short and I don't have the English word for that, which basically means short and crisp. And yeah, and we will go on with the light shader on the next video, which will definitely come very soon. So I think in this video we already got some interesting information. We took a look at the API parameters that we can get from Max. We saw how we can pass variables from one shader to the next, and in the next video we're going to see even more exciting things. Thank you very much. If you like this video, I remember you to maybe put a like on the video and subscribe to the channel and help Amazing Max stuff to grow. You can also support me on Patreon, which is of course the biggest help you can give me. The link will be in the description, and from Patreon you can also download patches and stuff, and you can chat with me, a lot of things. So see you definitely in the next video. Thank you for watching, and see you soon. Ciao.